Okay, so I will now introduce the third class of models, of flavor models, beyond the standard models. So we discussed the first time, maybe two lectures ago, we discussed this U1 model, remember? Then yesterday I introduced this MFB ansatz, okay, which is a completely different thing. So it's an ansatz about flavor breaking beyond the standard model. Now, what I will discuss is something that maybe somehow is in between, which is the idea of particle compositeness in explaining this flavor pattern for the structure of the Yukawa and the suppression of flavor changing currents. So, which is the idea? Let me first just the basic dynamical idea, which is very much connected to what you heard in the talk, the lecture by Sundrum. So the idea is the following: that there is some composite sector where there's a new strong dynamics and everything is strong interacting there, and there are some composite fermions which couple to the Higgs. Okay? Where an effective Yukawa interaction of this composite fermion with the Higgs, however, the true interaction is also the Higgs is a composite state in a sense, or at least it's very strongly coupled to these fermions. But then the coupling to the, so I denote here with the double line the composite fermions, and here with the single line the standard model fermions. So the effective Yukawa interaction, so the interaction of say Q and D to the Higgs is controlled by some mixing parameter. Okay. That's called epsilon Q and epsilon D. And the idea is that, okay, here there is strong dynamics, so here there are all order one parameter, maybe even complete anarchy from the point of view of flavors, you know, specific flavor structure. But the key feature of the hierarchy of the Yukawa is explained by the fact that there is a small mixing between these elementary fermions, which to a very good accuracy are the standard model fermions, and this composite sector. So you see that from this the idea that the Yukawa, in this case the Yukawa down, okay, is something that we can write this way parametrically. Epsilon Q I some Y star of the strongly interacting sector, and then okay. So the idea is that these things have this epsilon, okay, which is something that has three indices, okay, because so it's a vector in the SU3 space, or yeah, so it's a triplet in the SU3. Carry all the information leading to the hierarchy, okay. So the idea is that the epsilon 4. And so we have three for the quark sector. We have three epsilon, okay, one for the Q, the Q at the doublet, okay. So remember Q. Usual.
Sorry, I'm confused by the assignment of the indices right there.
Sorry?
I'm confused by the assignment of the indices right there because in the right side it says the number you use.
Here, yeah, this is a you're right. I am a bit sloppy. So if there was just a universal, total universal Yukawa, here there would have been no indices. Okay, that's one option. This, if you want, it's one possibility. Another possibility that okay, these things carry two indices. One for the okay, what this is really a mixing of these port I to the new state, and we call it Ni. Okay, and then this Ni coupled generically here. So I do not really think it has yeah, this state, let me call it N to I coupled to the Higgs, and here I have N to J and DJ. Sorry. So these states carry the same, maybe the same electroweak quantum number than this state here. Okay, but on the other hand, it's charged under the new strongly interacting sector. Okay, so the idea that here I can put here order one coupling different for the different generation. Okay, so in finally what I will use, and this is really on the minimal answers in this scheme is this idea, okay? That the UCAVA is given by this product of two. It's not. It's not a. These are two vectors. One can you think of as a column vector and the row vector. Okay. But really, this just gives the parametric scaling of the UCAVA. Here, there are order one factor, which I don't know, that depends on the strong derivatives. Okay. Which, in first approximation, I don't want to compute, and the idea is to see if we just putting this type of parametric suppression, we can explain both the structure of the UCAVA coupling and the suppression of function in the UCAVA. Okay, so we have three types of epsilon because we have the epsilon Q for the doublet, the epsilon D, and of course also the epsilon U. So like Q will be of the type epsilon Q times epsilon U. Okay? Okay. Again, I put this symbol just to indicate that this is up to order one factor, and these order one factors are not necessarily universal, okay? So it can be different for different IJ indices. This is what I want to mention with that notation before. And this is important, it's an important point. You see, it means that basically we have, now if you always keep in mind, the whole business is always about how we break these as to 3 to the 5 group, which is the fundamental group of the standard model fixed only. So here we break it with, for sure, these epsilon are breaking terms, okay, because they differentiate the various indices, and they transform now as triplet, not as 3 bar. Remember, the UCAVA transform as a 3 bar. Okay, so the UCAVA down transform as a 3 bar to 3D, okay, of this group here. On the other hand, the single epsilon transform only as a triplet. Okay? So I combine a triplet and a 3 bar to make the UCAVA. But then the fundamental things are these guy here. Okay, so that then in other process can appear in different combinations. They do not necessarily appear just in this project. You also minimum evaluation just keep the fact that they can always appear exactly in this combination, while here we separate. So we want a less minimal breaking. Not only, but here there is this order one factor, which means that in principle there are a lot of 3 bar terms that break the zero symmetry up to order 1, but they break it in the composite sector. So this fact cannot affect the dynamics of the standard model course, because to go to the dynamics of the standard model course, we have to pass these two guys here. Okay? Is it clear, the picture? And you understand that, of course, this is just really the most minimal scheme. Of course, one can make, again, more sophisticated model where one introduces an extended flavor symmetry where there is this symmetry acting on the standard model fermion, and then some other symmetry acting on these other fields. In that case, okay, then you can really classify these epsilon now as breaking term of the two symmetries and then classify also the UCAVA. But this, of course, requires much more assumption about the underlying theory, which I don't want to make. So let's try to see if the things work in the most minimal case, which is, I mean, if it works, it's good, because it means that irrespective of how these strong dynamics works, provided you have a small hierarchical mixing between the standard model fermions and the heavy fermions, you are fine. Okay, so these, so the idea is that these epsilon are hierarchical, so the epsilon can be Q, U, and D. Okay. If I look at the third generation, this is much bigger than the second generation, and is much bigger than in the case of the first generation. Okay. So sorry, I put the indices here up, so this is not epsilon 2, right? It's epsilon 3. So, and for convenience, I mean, one can always reabsorb the order one factor. It's convenient to define the epsilon. Let's define epsilon Q3 to be 1 and epsilon 3U to be 1. This way, I get no suppression for the topic of a cutting, okay? Which is the one that goes with the fields. Once I do this assignment, essentially everything else is fixed because I want to recover. So I know that what these guys are, okay, in the famous down or mass basis, I know that this is lambda d and this is dckn dagger upline, okay? Or of course I can make a rotation, I can go the other way, so I put this b here. So from that thing, it's trivial to show that these things are completely fixed. Because once I fix the normalization of these two, we can the epsilon q2 and the epsilon q1 must scale like the secant factors, okay? Because see, just look at here, so epsilon, if I look at same u, so same index 3 here, and different index here on the left, I simply scale with the secant factor. So this means that this is roughly VTS, and this is roughly VTD. Okay? That we know this is roughly Cabibo angle squared, and this is roughly Cabibo angle cube. And then, what about the other? The epsilon u I, okay? When I look at the diagonal terms in the Yukawa, the diagonal terms should reconstruct the fork masses, so I have that epsilon u times epsilon q is equal to lambda I, but lambda I is the lambda I, so it's the Yukawa tapping of index I, so in the case of the third generation this is 1, but in the case of second generation and third generation this is a very small factor. And so when this, and the same is true for the epsilon d I, and from this I deduce that I will put it here, that epsilon u I is equal to lambda u I divided by epsilon qi, but epsilon qi I know what it is, okay? So let me write as Vt I. Okay? And same for epsilon d I. And you can, if you put the numbers, you see that these are both smaller than 1. The mass operation is much stronger than the secant operation. Okay? And so it is consistent with this idea here. And the first thing that one realized here, one realized something very similar to what we already found in the case of the human model. That now, what is the Cabibo angle? The Cabibo angle is the ratio between the 1 2 indexes here in the mass matrix. Okay? Then, just take just look at y2 divided by y2 2. Okay? Here, so the index A is the same 2, so I cancel this, I just have the ratio of epsilon q1 divided by epsilon q2. This has to be of the order of the Cabibo angles. Okay? So I know that this by construction has to be the UD, and so I have a prediction that of this epsilon and this also has to be equal to. I always put these things because you see this is always upward the one factor that we don't control. Okay? So this is just epsilon q1 divided by epsilon. Okay? Because here I have epsilon q1, and here I have epsilon q2. Is it clear? So this is true generic. Now when I use the decomposition, since this is just, let me just write it explicitly. Using these ansatz, this is epsilon q1 epsilon u2 divided by epsilon q2 epsilon u2, and so it's like this, right? But then this, I already fixed these two, and I have that this is d over 1. Yes. And then so this is a prediction. A prediction that the Cabibo angle has to be equal to the ratio between the mixing between the. So the one missing is somehow of the same order of the ratio between the 3 to missing, sorry, 3 to 1 missing divided 3 to missing. This is a non-trivial prediction. Indeed, for example, we discovered already in the case of the U1 model, you remember? And the fact that it works, it's cool. It's okay, so it's something that goes in supporting this idea, and it works upward and one factor. It works. And you see, there was no reason a priori to have this prediction, because in principle, in a generic rotational matrix, we have 3 independent rotationalities which are completely unrelated. So the fact that this works is good. So you see, this idea gives a dynamic inside why we have this relation. And also, you want is also a dynamic explanation of why the first 2 generations are small in mass, simply because they are not very well mixed with these heavy versions. Of course, then you have to explain why they are not so much mixed. So you have not really explained it, but I think this is easier to explain. Just to explain the suppression and mixing, it's easier. Okay. And you get the prediction, which is so the prediction is the only trivial theorem. Now, let's see. Okay, since we already, however, got this prediction with the U1 model, let's see now if we have a better control of the Fourier change ultracurrent. So if we now go to build the famous tower of 5-dimensional operator, whatever. Okay, that's the usual stuff. So clearly now we can, okay, the new strong dynamics, we can make also 4 fermion interaction with couple more than 1, and then this can couple to our to our elementary values. Okay, so clearly now this is more dangerous because now we are not anymore protected by the minimal revolution ansatz, so this mixing can be big here, but okay, we are suppressed by this epsilon. And so we have to see if this suppression is enough parametrically to give it something comparable to what we have in the standard model. But so let's I guess it should be clear that it's convenient to look at, as we already done, to look just from the start from the bilinear structure. So the structure of type Q bar I Q J. Okay. Yeah, well, let's now put it really. Let's put it. So which epsilon should appear here? Well, of course, here this operator, for instance, let's consider this operator square is what appears in that level to up. No? So what will appear here? Well, in here, but before discussing the operator square, sorry, let's consider the linear structure. The linear structure has to be suppressed by epsilon q I epsilon q j. Okay. And I think it's interesting to compare what happens in this model with respect to what happens in the standard model and in minimal probability model, which is the same thing. Okay. So this is what happened in the case of let me do it. So in the case of partial compositeness, we have this epsilon q I epsilon q j. In the case of minimal flavor violation, to generate a structure of this type, remember I have to introduce u, y dot. So okay? And of course there will be more than one factor that we can control and blah blah blah. Then I can contract this with something else, but that's the interesting thing, okay? But now, what is this? That is the infinity yes, this is VEI star lambda dot square is J. And so, since lambda dot is more than 1, this is VEI J. And that's exactly the same thing, okay, here. So here we have VEI J. So this is very good. So in in the case of the U1 model, in this case here, we didn't have such a good suppression. For instance, especially if I take here S and D, so second and third generation, in the U1 model I was finding the complete language. Here on the other hand I find 5 power complete language because this is 2 times 3, which is exactly what we find in MFP. So it's good. So this partial compositeness idea gives a more efficient suppression of additional flavor changing structure with respect to the U1 model. So this is good. So for instance, then if I consider this operator square, which is the one, the dimension 6 operator relevant in the mixing, then I have this structure square, which is exactly what I have in the standard model. Well, with the difference that actually in mean of evaluation really it's exactly this combination. Okay, even the phases is fixed, and here the phases, for instance, is not fixed. So, but still it's another one modification. The parametric suppression is the same. Let's look at, however, there are cases where this is different. So let's look, for instance, now at this term here. Now, this is the downward field, okay? And what we have, so what we have, well, in mean of evaluation, this structure is miserably small because this is I have to put, sometimes this I call it right, like this. Yeah, I think on the lecture before I put the writing, so let's keep it. So this is lambda, it's YD. Why lambda? This is what one finds in the evaluation for this linear. Because to calculate the DNI, you have to put the YD. Okay. Then, of course, there is a first term which is YD, dagger YD. But that is diagonal, so it doesn't make the flavor change. So this is assume that I is different from J. Okay? So if I want to have I different from J, I have to put YD, 2 YD, but then I have to pass through YU to have a mix. Okay? And then if I put now the number, this is lambda d I, so which is related to the mass of the downward I. Then I have the usual factor, I, j, lambda d j, and then the lambda top square, which I need because it's over the one. Okay. But these two extra factors are very, very strong suppression. Indeed, this is why we never discussed purely attended operators in the standard model. Because these are, for instance, if I look at big bar mixing, I have a suppression of the bottom quark mass and the straight quark mass and the down quark mass. And this is totally nature. I don't see that we can neglect it. Okay. What we have here, we have, in the case of partial composite, we have what we have. We can write it this way. So we have lambda. Well, to use that, we have lambda d I, lambda d j divided by rho I. So you see this is much bigger here because now the silly factor here, the denominator. Now, however, still there is a strong suppression because of these masses here. Okay. Now, if you do the exercise and put the exact values of the downward, you have a coupling. So these are, for instance, let's be more concrete. So if I look at the case where let's say B but right, we have a new B right. What I find is the little coupling of the bottom, the little coupling of the down, divided by. So I have 1 over dTd dTd, okay? And then I have our MB divided by MB, which is the bottom little coupling, and MD divided by B. Now this is VDB is 1, okay? While MD is extremely small. If you put the numbers, this is really very suppressive. So despite it's not as suppressive as this one, it's still very suppressive. And you see, it's not larger then what you have in the corresponding left-left operator. And so, if I consider this operator, for instance, this operator square, okay, the matrix element is very similar to the corresponding operator left-left. Okay? And so, the fact that here I have a much bigger contribution, but still smaller with respect to this fitting one, it makes it not dangerous. Okay? Because anyway, there is the standard model contribution, which is coming from the left-left operator, which is dominant. I don't know if I've been clear. Is it clear this concept? So if I suppose I want to evaluate the amplitude of B bar mixing, okay? Then I will have my contribution coming from the matrix. So I have my effective Lagrangian will be the contribution of the left-left operator times the left-left operator, where the left-left operator is just simply this one squared, okay? And I should put the lambda square in front, plus I have the right operator of right divided by lambda square. Okay? And finally, so my amplitude will be C left left, the matrix element of O left left, I write it generically this way, plus the matrix element of the right side, all divided by lambda square. Plus there is a standard model contribution. Okay, so this is what the DSM. Plus there is a standard model contribution. Like C standard model, lambda standard model, and is of the type left-left. Now, we have seen that the coupling of the left-left operator is very similar to the standard model one, okay, in terms of parameters of flexion. Now, if the right-right coupling, okay, is similar to this one, the matrix elements are similar, okay, that's not a problem, okay, that's what I want to say. So here we find a coupling which is significantly bigger than NFV, however, it appears with an operator that has a matrix element similar to the one that we have in the standard model, so there is no way to see that there is this species, okay, that is not present in the standard model. Well, unless you give me a very precise measurement, but it's parametrically, okay, it's consistent. Okay. Finally, actually, the only case where really we are in trouble is the case of the left-right mixing. Okay, take it here. So operator like B bar, scalar operator like B bar, I, 2 plus J. So what you have here, in minimum evaluation, we have we know it's lambda, it's y, d, y. Okay, this now should become clear. So this is the Ikawa coupling of the down index I, and then I have my usual v t I v t j times lambda top square that eliminate and we get the star. So this indeed was exactly the same combination we found for bitless gamma. You remember? So that was lambda b. Okay. Now in this model we partial composite of something different because we have okay. That I erased it, but I remember that this is lambda di divided by v I. Okay. And then times I have v j. Okay. Clearly this is different because VTI instead of being a denominator, now it's denominator. Now let me be more specific. So let's consider explicitly two cases. So let's consider first the B bar I, the B case. So I take index I equal to 3 and index j equal to 1, I get this, okay? Which are the two fractions in the case of minimum evaluation or standard model, I have lambda b, VTB, VTD, okay? But in VTB it's about 1, so it doesn't make sense. In the structure, composite test I have lambda b divided by VTB, VTB, so VTB 1, so again, more or less the same. If really up to order 1 is the same. So this operation here again works, seems different but works well. What is not the same is in the case of faculty instruction, but now for the case S right left, okay, which means I equal 2 and J equal 1, because in this case I get lambda S dt S dt, e facciamo qua sempre che lambda S dt divided by dts. Okay. And now this is a big enhancement because I have one of the BTS and BTS is a small quantity. Still, before concluding that we have a problem, we have to compare with the leading structure, which is the S bar left, D left that we have in the standard model. Okay, so whenever we have a transition with type S to D, okay, we should look at what happens if it's not obscured by the standard model contribution here. And in this case here, what we have is BTS, BTD, which is numerically quite close to this. Okay, it's a good exercise to read the numbers here to do exactly the thing. You will find that after the factor value, this is just a factor 2 bigger than this, so it's not a big issue. However, which is the big issue? The fact that now the matrix element are very different. If you remember when we discussed, the matrix element for scout current, I told you that it was this enhancement, so-called current enhancement of the matrix element of this operation. I think this was maybe 3 lectures ago. Okay, if you forget it, I tell you once more. So what I mean is this, in particular, if I look at this operator, okay, K on top, and right in there. If I look at this matrix versus, I want to do this versus okay. What happened that I showed you, I told you, okay, a way to evaluate this, at least parametrically, is to insert here the vacuum. So to write this as the product of K S bar D left vacuum, vacuum S bar D K bar, okay. And if you remember, if you look back to your notes, you find that this was proportional to mk squared divided by ms. And now this appears twice, squared. This is a big enhancement. It's a factor of 5 squared is a factor of 20. Okay. And this is the fact that, okay, even if the two have similar coefficient, then this one now gets a big enhancement, but this is say, the same units. This is over the k squared. Okay. But this is a dimensional. Okay, to be precise, here, if you remember, there was here the fk, and here there is fk squared. If you look back to your notes, you should be able to check this. And so here, this structure is very dangerous because this operation, okay, is not enough, okay, compared to the leading terms in the expansion, and also because it comes together with a big matrix element. So, at the end, it's not bad. So basically, there is only one case where really one failed by a factor of 20, okay, in terms of suppression with respect to, that means that the effective scale has to be heavy. What we want, when we now build the effective theory for this type of operator, we have to be sure that the dynamics do not generate this operator, operator line. The dangerous operator is this one. So, for instance, the really dangerous operator is this one, as right, left, as right, so it's suppressed here by the epsilon Q1, epsilon D2, epsilon epsilon Q1, and oh no, sorry, here this operator, so here it's not the good, so here the right to be consistent with the second right. And here I should put epsilon. By the way, the operator want to build is as far right, the left, as left, the right. So here it's a bit sloppy because this operator, see, this operator is not a superinvariant because that's only the left field. Actually, the most dangerous operator is this one. Okay, but okay, the argument is the same, but sorry for this. So, I mean, what I want to say, okay, here there will be some suppression scale related to the new dynamics. Okay, if I just put in the parameters of question given by this epsilon, I find something that is too big and it's not compatible with the effective scale of it. Okay? So, maybe, if I build now the explicit model, I have to be sure that the dynamics generating this operator is generated with a sufficiently small coefficient. So I need some tuning. So we discussed about tuning in effective theories. Here we need some tuning okay, of the coefficient operator to be consistent with the data. If we want to keep this effective scale relative. Okay. Is it clear? So this is, again, was the third type of example I want to give you of different, okay, answers, okay, about the mixing beyond the standard model, and as a way to address this problem of trying to explain the U-task, but also give you a suppression function. Yes?
Yeah, sorry, you have said that we need some tuning on the epsilon factors.
No, the epsilon factors I cannot do, they are what they are.
They are fixed.
Is this coupling here? I don't know. I mean, what?
The overall coupling.
The overall coupling. You see, I don't know. So far, I've been as general as possible without specifying exactly what happens here. So maybe there is an exchange of some resonance, or maybe this answer to this is forbidden because the appear of the loop. I don't know. Okay. So for instance, if I build the model such that this amplitude do not appear at the tree level, appear on the loop, but that's already maybe it's a good possibility. Okay. So this would be a way to tune to be small this coupling. So when I just write this, so what I know that parametrically these things has to be epsilon Q, epsilon B, epsilon D. So it will be 1, 2, 1, 2. Okay, because I have. Parametric, then will be some order 1 factor, which I don't know. Okay. So this order 1 factor is the one that I cannot compute just using this generic symmetry argument, okay? Or generic symmetry argument. So to compute this coupling here, I really have to specify which is the dynamic, which are the new degrees of freedom, how they interact, so how these heavy fermions interact with each other. Maybe there is some technique rho, or maybe there is some technique gluons. I don't know, so I have to specify. Once I specify, I can compute, and okay, naively I would expect something more than 1 if there is a new strong interacting sector, but maybe accidentally in one of the amplitudes there is a cancellation, it's not 1. In that case, I'm fine. That's what I mean. Usually we don't like accidental cancellation, okay? This is why, I mean, all the the story is that here we would like to avoid accidental cancellation. But of course, in a specific model, you can compute and see if it is there or not. Usually, it's not. So if there is a cancellation, at least the cancellation is stable with respect to the data correction and so on, if there is a symmetry happening while this cancellation is there. And this is all the philosophy of quantum field theory. Especially if you have a strongly interacting sector. If something maybe is zero accidentally at the first order expansion, then you will have radiative correction. This radiative correction will spoil the zero unless the zero is protected by a symmetry. Okay? For instance, radiative correction cannot cancel this suppression here. This is why I'm planning to understand that this suppression is not. Because I know that this suppression has to be there. Okay, it's there because my field, my external field, coupled to the rest of the world only via this couple here.
But this cancellation should enter only in the case of the SD mixing, right, and not in the BD.
Well,
So
I mean, it has to be at least there. I mean, it is also in other places, fine, we don't care.
And doesn't it imply a new flavor structure of the strong dynamics?
Well,
Because you are distinguishing two different cases.
Yeah, for instance, one of the possibilities would be to impose some extra symmetry on the flavor structure of the new field. For instance, to impose a symmetry such that those of the first two generations, maybe there is some hidden SU2 invariance where the 2 refers to the first two generation, which forbid the discovery. Okay? That's a way to do it. So, if you make more answers, then you can explain more suppression. But you have to make a specific answer, for instance, to impose an extra symmetry. And indeed, actually, that's exactly, it's a good point, exactly one of the ways, but that's strong, to impose an extra symmetry, forbidding this diagram in the limit of exactly some extra SU2 acting now on the heavy guys, right? Yes, sir.
I would like to know if the minimal flavor violation answer can be implemented in strong interactive extensions of the model, or only in SUSE models.
It can, actually, there is here Michele who did it as an explicit construction. You can do it because, for instance, if you see what one can do is, for instance, if we extend the theory, okay, if we introduce other field, as I was mentioning briefly, we could impose an extra symmetry on the flavor structure of this other field, okay? Then, when I say, okay, the Yukawa couple is of the type epsilon q times epsilon q, okay? And then it says, okay, but this one here there is this y star from the strongly interacting sector, okay? Well, one can say, if, okay, let's now assign a transformation property to this guy here, okay? And then in this case, so using my global flavor symmetry will be SU3 to the n times, sorry, SU3 to the fifth, times an extra, suppose that I have only 3 generations, okay, for this other guy, times an extra SU3 heavy acting only on these other guys, okay? Then my epsilon 2, in a sense, are promoted now to be 3 bar terms because they transform under the capital D to the heavy guy. Okay, so this will be, and then you should treat this as a, so this will be epsilon qi, let me call it h, where h is the index here. Then I have this y, h, g, and then I have my epsilon q. G, J, okay? Then I should define how this symmetry is broken. Okay, for instance, if I say, okay, these things, it's the symmetry SU3H is not broken at all, then this has to be, for instance, identity, because there is an exact symmetry here. Then I can also say that maybe the breaking terms here in the epsilon u right are also, say, proportional to the identity. It's an answer, okay? Then what I found is that basically I have only a one-to-one relation between the epsilon u and one of, sorry, the yu and one of these epsilon 2, and then maybe in the down sector I have epsilon 2 and epsilon d. So basically, you have exactly like in MLV 2 3 bar terms that break the symmetry. Okay. So this is just one explicit way, but so can be implemented. Of course, you need a bit more sophisticated construction. You have to define, for instance, in this class of model with partial composites, you have to define how the composite state transform under the symmetry. Even without speaking about composite state, it's clear that if your composite state transform under this symmetry, and you decide that your symmetry is broken only by the usual coupling, you can do it. You can do it at the level of the effective theory. To really build explicitly the dynamical model is another story. Okay? That is complicated. There, I think the most natural way is what I briefly sketched yesterday. That is, maybe in linear relation it's an accidental symmetry because at some scale you generate as a relevant operator only those analog to the usual. That's, I think, is the most natural way to build anything. So, for instance, again, at the heavy scale, where there is only the dynamics of these heavy fermions, you build the model such that the only relevant operator are those which have transformation properties like the coupling. And no more, simply not more because of you cannot build other relevant operators. In that case, whatever creates the fluid symmetry will be projected into the Lyell structure. Okay. And that's it. That is the most powerful way to code it. You don't have to worry about Boston bosons, anything. Okay? But if you want to really, that is a statement about which, I think I really see MLB as a statement about which are the relevant flavor-making operators in the ultraviolet. Okay. For instance, this one can really see it in case of supersymmetry, but one can impose it in the case of opposite. Okay. And so, again, one can build many variations of the theme, one can go to S2 similar, so, but the basic idea is this is why I wanted to illustrate this type of cases. Of course, this is a more dynamic approach, okay? We really try to avoid imposing the symmetry, just impose one dynamical principle of the suppression of the mixing.
Is it possible to have problems with CP evaluation?
Yeah, of course, CP evaluation is always more delicate. But CP evaluation we should distinguish two cases. I mean, CP evaluation in flavor changing process, which is the case where CP evaluation has been observed so far. So far, CP evaluation has been observed only in tricky-bar mixing and big-bar mixing and in some BD case, okay? So always in a flavor changing transition. And okay, it's the standard model. In those cases, I mean, CP evaluation comes from the CK phase. It's the only CP relative quantity. And of course, in MLP, construction BB type, also you have circulation only from, but it's not totally obvious because I mean you can also write new flavor blind terms, flavor conserving terms, with if you write a non-admission operator, which however is flavor conserving, you can put a phase to this operator. And this phase could contribute. Okay? So one of the problems of manipulation is that not necessarily imply a suppression of flavor conserving process, okay, possibility. So you have to, that's an extra assumption. I mean, so you can make the assumption that both the flavor symmetry, so the S2 and the CP symmetry are broken only by the coupling. So in this case, of course, by definition, you are done. But it's an extra assumption, so you have to assume that, yeah, these NCP and CP in this case, symmetry, both broken only by the coupling. If you don't do that, you do have problems, typically in observables which do not violate flavor, like the electric dipole moments. Okay, so the electric dipole moment, of the down port is an operator of this type. If I write, now D is really D, so index the same flavor index. Okay. And then I put so that's a dimension 6 operator that break no, what this okay. in linear notation, since you come to the right, to the left, you have to put here y d. Okay, and that's true not only in linear relation, but this is also in partial component, also in the case of the Hugo model. You have to do something of this size. So here, the index 1, 1, 1, 1. But 1 is enough. Okay, you don't have to put what you want, because this is flavor conservative. And now here I can put the phase. Nobody forbids me to put a phase here, an extra phase. Okay, if I do that, in this phase, I have problems. Okay. And that indeed is one of the open problems why NFD intended only as this type of, protecting only this type of symmetry, imposing that is broken only by the Yukawa, do not forbid this phase here, and that space experimentally turn out to be small if you want to keep the lambda. So that is an open problem. There are ways to address it, of course, and to use about require more assumption. Okay, so now in the last part, I want to discuss some, basically, closing this chapter of models, and now go back to the phenomenology, discuss a few observables which are interesting, which I didn't mention so far. Unless there are other questions here?
No, yeah, just understand, that is the standard model Yukawa,
yes.
Right? So inside I can reproduce it as a northern one Yukawa with the two epsilon factors.
Absolutely.
Okay.
So,
can I imagine that phase factor comes from the probably random phase factors of these Yukawa inside?
Absolutely, exactly. So for instance, in case of partial composite, it is really natural to have this phase here. Because indeed, there is no argument why. And of course, you have to do it with an operator of this type that has to be, that is a non-addition operator. Okay, so if I have left, then it is cancelled. But with the right left, I do have this problem. I mean, again, unless I do specify more the dynamics of my heavy field, such that I forbid this phase. Because of symmetry. One can do it, but in a sense similar to what I discussed before. So you have to put an extra symmetry in the strong sector to forbid that. Okay. Okay. Okay, so the first observer I would like to discuss is this decay. The decay the S or VD going to electron pair. Because this is really the Gaussian channel of flavor violation of rare decays at LCB. Okay, at LC. Okay, because at the LC, and we know one lecture about physics at collider after the lecture by Strasser. So you know that it's a very complicated, dirty environment because of so many interactions and indicators going around. But this process it's very clean because you can select the two leptons in different states, especially when these leptons are, let's be more concrete, muons. Okay. When these two leptons are muons, the muons you isolate them very well, even same as an atlas, even better at the ACB, and then you impose that the mu and variant mass reconstruct the B meson, you have plenty of B meson, so you can search this decay even if it is extremely suppressed in the standard model. Okay. And it has been observed now recently. This is one of the highlights of LC physics of last year. So let's look at the effective Lagrange in the standard model. Poi compute this amplitude in the standard model, okay, we have to do the usual calculation. Each one of the diagram I will show you in the first lecture. So here we have B left, I can write it in the standard unitary gauge, okay, so here we have the top, U, okay, and here we have the technical generically D, given and X of D. Then there is also the block diagram there. Okay, first diagram at the top, U, and then the trio coming down. Okay. Well, what I can do the calculation is the standard calculation with the top dominance. So if you find the calculation in standard model, we'll find something that is a coefficient that depends, actually it's called C10, depends on the top mass divided by the dummy mass. Okay, compute very precisely. Then, of course, you expect the 16 pi square, and we know that I can write it this way. Okay, I can absorb all the one factor here, and here I have so 2 with cap equal to g square here. And then I have this is the usual top structure, so I have VP star, VP3, okay, lambda top square. It's exactly like, I mean, I think we discussed the first day the Z-penguin amplitude, no? That's exactly, it's a Z-penguin amplitude where the Z-penguin then is contracted to the new line. So finally, when I contract and integrate out also the Z, I recover this structure. In this level, and nothing else, right? Plus. And I can compute this very precisely. So let's look at the decay amplitude, okay, because this case is really simple. If we look at the decay amplitude, I have to take the matrix element of this operator. So let's forget all this part, just look at the amplitude is proportional to the matrix element between 2 muons and this divided by the left and the meson. Of course, this is a matrix element trivially factorized now, exactly factorized in terms of 2 vacuum insertion matrix element. And so the non-trivial hadronic matrix element is the matrix element between this current divided by the vacuum, and then there is this other one which I just write as divided by well, these are the spinor field, okay? But this matrix element, we have seen it. This is the matrix element of the left-handed current between P and the vacuum. Actually, only the axial part contribute because this is a pseudo-scalar meson, so this is just E F E. But there is one alpha to be precise because here there is the left-handed projector and then there is the B momentum. Okay. But the B momentum P in this process is exactly the sum of P mu plus P mu bar, right? So here, usually there are confusing notation, but here we will put L. Here. So the moment of the guy is just the sum of the moment of the two put P plus P minus. No, here. Okay, then, so I can compute this. This is just I mu bar left. Well, I need to write it explicitly with the projector. This is gamma mu 1 minus gamma 5, and then I should start to contract gamma mu. So I have P plus slash plus P minus slash gamma mu 1 minus gamma 5 mu. And then it's another factor 2, so this is 4. And then you see that I can use the equation of motion of it because these are the moment of the muon. So this is exactly, and you see that the vector part cancel, and what remains is twice the muon mass. So I get B2, sorry, 2 already cancelled, and mu bar up to maybe this. You see the peculiarity of this process triggered by the fact that the new momento is equal to the sum of the two left momenta, is that the amplitude is proportional to the new mass. So this is why it's very suppressed, because it goes to 0 in the limit of 0 new mass. And this you can understand it here just kinematical, because you have a scalar particle getting into muon, so they want to have opposite helicity because sorry, they want to have same helicity because this is a spin 0 decaying. But and then of course this is so you, and this is the pressure because one is a muon, one is an anti-muon, and so you get something proportional to the new mass as it should be. So this goes to 0 in the limit of 1 it should be mass. But then, why I did all this? Just to show that a usual is a gaugeless limit of the calculation show things in an even more transparent way, because we can do this calculation forgetting about gauge interaction, just looking at the gaugeless limit. So let me erase this. So you know that the amplitude is proportional to the new mass, okay? And then the carbon fiber moves. And therefore there is all this coefficient involved. Let's look at the process in the gaugeless limit. What happens is that we have here our Boston boson from the current interaction. So here I have a B right coupled to the top left, so it becomes the top right, and this is the down left. And then it's the Boston boson component of the Z here, that's coupled to the left and the right. So, a completely alternative way to see why this new mass appears here is just because at the end what matters is this type of sub-contribution in this genetic calculation. Is the one where I select the pseudoscalar component of the Z. It's Gaussian boson component, which happens here with the new mass. See, if I compute this up, what I get? Well, here there is the usual loop calculation, that is 116 pi squared. Then I have here, you see, here I have y down, because it's b right, b left. Here I have y up, that is y up down, and here I have y up. Okay? So I have y down, y up, y back, index 3, 1. Okay? And this is a dimensional quantity because it's a gap between fermion and scalar. So it's like an effective Yukawa interaction, so there is no extra strict scale separation. Then I have the propagator. Okay, usually I omit the order one factor, but however you can compute them. It's not complicated. Actually, it's a good exercise. Then there is a peculiarity of this process that you don't see anywhere else. That you have this propagator of this Gaussian boson not inside the loop, but at 3 level, which is kind of remarkable. And now here I should put the propagator here of this guy, but this guy is massless because you are in the gaugeless limit. No? So I'm working limit no gauge, that is the Gaussian bosons are massless, are not eaten by anybody else. Okay? So here I have 1 over the square. Okay, question? And then I have the mu Yukawa. And then I have mu right. Sorry, and then I also, of course, I have the parts which are B right. You see, apparently there is the structure, but actually that structure was hidden here. Say we couldn't see it because we're working painful here, it's more complicated to see it. Now, so we have this amplitude, and let's now look at the matrix element. So here we have to look at the matrix element between the vacuum and the right, the left, and the B-meson. There's a different matrix element. This matrix element, we have seen it, it's FB and B squared divided by and B. Remember, we demonstrated this just taking the derivative of the axial current. So it is a factor because this is just the electric. And so then if I now look at the amplitude, taking the matrix element, so we want this is the amplitude partonic. And now the derivative for B going to mu is 1 over 15 pi squared. I have this factor here, which is exactly the same sort. Look at it. This is dt, d star, dt, d, lambda top squared. But then I have this lambda b, the bottom of our coupling. But what is lambda b? This is just mb divided by b, the vacuum expectation bar. Okay? Sorry, right. So this is lambda b. Then I have 1 of the square, which is 1 of b squared, other mass, because the momenta is exactly the momenta of my head. Okay? Then I have yu, which is m mu divided by b, because it's just the diagonal in the vacuum. Okay? And then I have my matrix element, fb and b squared divided by and b I omit the one factor. And so that you see the miracle, I get so other mass, work mass, I get mu, the b squared, so the b squared is exactly what I have here. So now everything is exactly like this, and then mu fb, and then of course I remain mu by that. Right. So I get exactly the same structure that I had before. And of course here, by parity, only the gamma factor supply. Okay. So, okay, this is just a trick to show that one can calculation is simple way. But beside the trick, what is relevant, you can understand much better why this process is interesting. What is interesting is if we modify the Higgs sector here, we can have, for instance, we go to the cases which I discussed yesterday briefly, the case of more Higgses, okay? Well, I can still have this diagram here, but now with the heavy Higgses go here. What type of amplitude will I get? Sorry, before discussing the heavy Higgses, actually still in the standard model, there is not only this guy here. Of course, given this, the peculiarity of this process that we have this neutral propagator, of course there is also the physical Higgs here. So there is another amplitude like this one, but with the physical excitation of the Higgs field H. So what will generate that? The H, so the physical boson, is coupled here exactly with the same coupling, however it's suppressed by its heavy mass. So this is a very tiny fraction, because if I just say like this calculation I cancelled here there was this square, so I have the phi 0 give a propagator which is mb square, okay, but then I compensated because of the matrix element, but then the physical Higgs, if you compute it, give a contribution that goes like, well, p square minus mh square. Okay. So when I factorize the leading part, I get 1 plus, 1 minus, which is clearly a very, very small fraction. So this is the carbon mass divided by Higgs mass. So this is 5 GeV. Okay, it's not 0, but it's 5 GeV divided by 100 GeV, it's very small. So, but in principle, if one could measure this tu preferisci no? Spent to better effect on the street, which is impossible. If it was possible, one could see the fact that there is a Higgs propagator there. So that's it's a lie. This will never be possible just because it will never be able to reach that precision. However, you see that now, so it's small, and that's this standard model. But now if there is another state here that coupled with modified Ikawa coupling, that could be a bigger effect. Because, so that is what? The Higgs now suppose there is a new heavy Higgs, which however have coupling here which are not exactly the standard model coupling. Even, for instance, we have seen yesterday that even in uniform regulation, it's easy just to shift overall the Ikawa coupling. Maybe, for instance, if this is in the 2 mode, here you expect a tangent bit enhancement, but this enhancement is just the enhancement of the Ikawa coupling of this, for instance, what happens in supersymmetry. In supersymmetry, you want to find out that there are corrections here. I don't do the calculation because it's more complicated, but in SUSY, you find that there are corrections that goes like tangent beta cube, okay, divided by the mass of the heavy Higgs, okay, times some epsilon complicated factor depending on the structure of the model. But you see, this tangent beta is something that could be even factor 10. So this is a big enhancement, okay? So, parametrically, it's again, NB squared by tangent beta. And this is a big enhancement that can compensate this big suppression here. And so, if you want, it's a I really like this problem. Just to see, I mean, you see, it's almost like a way to identify Higgses, okay, but projected at very low energy. And you see the coupling of the Higgses to light state, like the muons, that so far has not been proven at the LHC. Actually, maybe this is a good idea. One could even, I think, if one want to put the bound on the coupling of the physical Higgs to muon, one could use the formation coming from the mu. Because, okay, if you assume that the coupling of the Higgs, sorry, here the Higgs are coupled to the top, okay, this coupling we have measured already. Roughly measured at LHC. This coupling not. Okay. In the standard model, we know that it's very small. Suppose that this is not really the standard model Higgs. Then from the measurement of mu, I think you can put the bound here. This coupling cannot be too big because otherwise you destroy the agreement. Maybe we should like it. Okay, so let's look just an example of why this process is really very, very clean as you see. No? Because another thing is also interesting that you can measure both the B sub S and the B sub D. Okay? The two different measures where the spectator is the S or the spectator is the D. Okay? And so, then looking at the ratio of the two amplitude, that's a really very good way to test minimum field violation, because if there are extra X's and so on, whatever, that modify the amplitude, you expect that if there is minimum field violation, still the relative coupling between B sub S meson and B sub D meson is just controlled by the secant structure here. So if you take the ratio, you should cancel the increase coefficient and just find something proportional to BTS and BTD. So measuring precisely the ratio of the amplitude is a way to test and if one day we will see deviation. Okay. I think probably is one of the best, potential best tests of these answers. Okay. Are there questions here? Okay, as a last phenomenological, I'm doing a phenomenological application. As a last phenomenological application, I want to discuss something that was related to a question that somebody asked some time ago. That is, how can we measure the phase of the secant matrix from three-level process? I know, maybe you asked that somebody in that direction. And that I think is an interesting question, because we would like to have really a determination of the phase from process not affected by new physics. So it would be good if we can find observable sensitive to the phase of the Siegel matrix by generating a tree level in the. And there is a way, an interesting way to do it in the standard model. The way is the following. So let's look at these two triangle. Just a 3 level decay B going to C, okay, and then well, this is a BD. I generate a C and an anti-U. I generate an operator of the type P bar left. Or I don't even want to write this later. So I just have here a decay B equal to B C U bar. Okay. Now I can consider this other process B which is B going to D U bar C. Okay. Okay. So instead of having here C U bar and here I have C bar here. Okay. Now here I have the coupling is BCD and here the coupling is BUD star. So this is a leading transition that is of order lambda square, while here on the other hand I have BUB VC B star, which is something of order lambda to the 4th but with a phase. So here I have VUB, which in the standard parameterization is kept the phase of the Siegel matrix. Anyway, the relative phase between these two in a model independent, like phase conversion independent way, the relative phase between these two is the Siegel phase. Okay. Now you would say, okay, these are two different processes, so they will never interfere because here I have C and here I have C bar, so how they can interfere? But they can interfere because there is DD bar mixing. That's the thing. So I can have DD. You see here, this can make a D meson, this makes a D bar meson. Or maybe we have called the opposite way, it's always a confusing thing. But okay, certainly one is the opposite of the other because there are C and C bar. But D and D bar meson, D and D bar meson oscillate exactly like KK bar, K bar, and so on. So far I didn't mention too much about DD bar mixing, so I stressed very much KK bar mixing, DD bar mixing, and so on. Why? But because DD bar mixing, the mixing of meson composed by A type, it's a mess because it's completely dominated by long distance, so we don't compute it precisely. There is no top contribution, so let me open a parenthesis here where I compute this amplitude. I try to see. Here what runs inside this group are B, S, and B also runs inside of the double clocks, not here. So there is not anymore the large uptime, the large Yukawa current on the top that selects the leading contribution, because all this Yukawa current are relatively small. And actually, the bottom Yukawa current is the biggest one, but this is strongly suppressed by the hierarchy. Okay, so here the deep world are suppressed by B, C, D, U, B, which is the 5th power of KB1 angle, while the other hand, if I put S or D, I have only 1 power of KB1 angle. And since the deep world mass is not so big, the enhancement again here is not competitive, and so what dominates are the light clocks. Okay, so this process actually proceeds basically via pure long distance of intermediate state hadrons make an important contribution. So it's a suppressor transition because it's second order in the weak interaction, but it's to very good accuracy CP conserving because only the first two generations are involved. So it's CU and SD. So to an excellent accuracy is CP conserving, and but it's not custom. But it's measured. It's there. It's present. So what happens that B can go to D via this amplitude, or can go to D bar, but then D and D bar can mix, and so they can both decay to the same time state F. Okay. So, well, you can measure, for instance, equal to X plus D and X plus D bar. Okay. F plus X. So this is the trick to have the interference of this amplitude. Okay? Because here you proceed with one amplitude to produce the B, in the other case you proceed with the other amplitude. So here we proceed with an amplitude which is it's A weak. Let me call it this is the A weak leading. You produce with the A weak suppressor that has a factor equal to I. Yeah. Okay, so clearly the interference of these two is sensitive to gamma. Still, it is not obvious, okay, that you can single out gamma because this is a totally hadronic amplitude, so it's very complicated to compute. But all the rest can be determined by data. And this is, let me be more precise. So here, okay, what we have. So in one cases, okay, we have A weak, okay, time A of D equal to F. In the other cases, we have the A weak leading and then you have the A D bar equal to F, and here you have this phase. Okay. Now, this amplitude, I'm going to take the modulus of this amplitude you take from data because you measure the width of D equal to F. Okay. You can measure just looking at you can measure this amplitude from other processes. From this you determine the modulus of this amplitude. Okay? You don't determine the strong phase. There is a strong phase, but you determine the modulus. Then you can also look at other processes, where you go for instance X plus a final state accessible only by D. And here you can look at a final state accessible only by D bar. So for instance, a D decay with the let me call it the DL plus, okay. So you see, if a dimension decays semi-electronically from the charge of the electron, I determine if it is a D or a D bar. So I can also measure separately really the strength of these two amplitudes. Because again, I can measure the decay amplitude of the D separately, and I measure this process, and then I select a case where I target the flavor of the D. So I can really measure all the modulus involved just by other process. Okay? So then I remain only with the. So I pin down exactly all these things here from other observable, and then I remain only with the weak phase and the strong phase. Okay, but then simply just looking at the sum and the difference of the two decay rate, okay? Oh, sorry, then I have to look at the bar, okay, where I exchange instead of B an anti-B, and what happens when I exchange B for B bar, that I change the sign of the phase. So I have exactly all the same, but if the I gamma goes into equal minus I gamma, while the strong phases do not change. Okay? So I have a set of 4 amplitudes where I know exactly all the modulus from other observable, then I construct the difference and the sum, and then determine the two phases, just an algebraic exercise. You see, free of uncertainty, because you free of uncertainty, just taking all these things from data, you can solve an algebraic problem and determine this phase of the Secant matrix just looking at processes which involve a triangle atom. Okay, so I don't do the exercise, that is just atom, but for the concept it's important. The concept is that you take care of a phenomenon that is the interference of the bar that you can measure from other processes that leads to the interference of amplitude CSI. And of course, the crucial theoretical input is that you know that there is no superior ratio in digital mixing. Otherwise, this would spoil, okay? When I go from here to here, I also would have to change the phase of digital mixing. But this I know, actually experimentally, one can check that the phase of digital mixing is extremely small, less than 10 to the minus 3. So, to that level, accuracy determines the phase in the sense.
So this will be possible? Or?
No, this is done right now. Exactly, this is how. I mean, that's really. It's complicated, so it requires significant statistics. But this is the way now the phase gamma is determined. So if you look at all these CKM plots, and that is the band of UV. Okay, there is a band here, what they call gamma. That's exactly how it's determined with this. And so this intersection of gamma determining this way and UV that is determined again from 3 level process, so basically is the same electron decay E to U electron neutrino. These are two 3 level observable. So the most conservative determination of the CK matrix just using 3 level is now done. And of course this is an error which is bigger than the one when you combine all the other observable. But of course when you combine the observable, you need to assume that they are not polluted by new physics. This is Vipermisi and so on. We've seen that it's likely to have maybe a small new physics contribution. So in that case, in that case you cannot really use it to determine the phase here. On the other hand, this observable really you expect that the physics contribution is extremely suppressed. And this is why we can then put very solid bound on the physics contribution of the atoms, because we know that we determine the phases in a model independent way.
Okay.
Okay.